Quantum superposition. In the classical sense, a coin can land on either heads or tails. However, in the realm of quantum mechanics, particles can exist in a superposition, a state in which they are effectively both heads and tails simultaneously, at least until an observation is made. This phenomenon is not merely a matter of uncertainty regarding the outcome. Rather, the particle genuinely occupies multiple states at once. Such a peculiar occurrence challenges traditional logic and prompts a re-evaluation of our understanding of reality. To comprehend superposition, it is essential to recognize the probabilistic nature of the quantum world. In classical mechanics, the behavior of objects can be predicted with accuracy if their initial conditions are known. For instance, when a ball is thrown into the air, its trajectory can be calculated precisely. In contrast, particles such as electrons or photons in quantum mechanics do not adhere to specific paths. Instead, their behavior is described by a wave function, a mathematical representation that encompasses all potential states a particle may occupy. When we assert that a particle is in a superposition, we indicate that its wave function embodies multiple states at once. A well-known thought experiment that exemplifies this idea is Schrödinger's cat. In this scenario, a cat is confined in a sealed box with a vial of poison that will be released if a quantum particle within the box decays. The state of the particle, whether it has decayed or not, is determined by quantum superposition, meaning it exists in both states until an observation is made. As a result, the cat is considered to be both alive and dead until the box is opened and the situation is observed. While this thought experiment may seem absurd, it highlights how quantum superposition can lead to paradoxical outcomes when applied to larger objects. The principle of superposition was first articulated in the early 20th century as physicists sought to understand the behavior of particles at atomic and subatomic levels. Experiments involving light and electrons, particularly the double-slit experiment, demonstrated patterns that could only be accounted for if particles behaved as waves. When electrons are fired individually through two slits, they produce an interference pattern on a detector screen, a clear indication of wave-like behavior. This pattern arises only when the particles are in a superposition, effectively passing through both slits at once. Quantum superposition is not merely a theoretical concept. It has been confirmed through numerous experiments. For example, in 2010, researchers at the University of California successfully created a superposition state in a small metal paddle, an object visible to the naked eye. While not as large as Schrödinger's famous cat, this experiment illustrated that superposition extends beyond the microscopic domain and suggested a connection between the quantum and classical realms. However, the question of what occurs to a superposition upon observation introduces one of the most enigmatic aspects of quantum mechanics. According to the Copenhagen interpretation, the act of measurement causes the wave function to collapse, compelling the particle to adopt a specific state. Prior to measurement, the particle exists within a cloud of probabilities, but observation narrows it down to a single outcome. This raises significant inquiries. What defines an observation? Does consciousness influence this process, or can any interaction with the environment lead to the collapse of the wave function? The interplay between superposition and measurement has practical ramifications in areas such as quantum computing, where quantum computers utilize qubits that can exist in superpositions of 0 and 1, in contrast to classical bits that are limited to being either 0 or 1. This property enables quantum computers to execute numerous calculations at once, significantly enhancing their potential for specific tasks. For instance, superposition allows quantum algorithms to factor large numbers or search databases at an exponentially faster rate than classical algorithms. Additionally, superposition is crucial in quantum cryptography, providing unparalleled security for communications. In protocols such as quantum key distribution, The superposition states of particles are utilized to encode information. Any attempt to eavesdrop disrupts the superposition, making any tampering detectable and ensuring secure communication. One of the most fascinating applications of superposition is found in the field of quantum biology. Some researchers suggest that phenomena such as photosynthesis and bird navigation may involve quantum superposition. In photosynthesis, for example, superposition could facilitate the efficient transfer of energy through a plant's light-harvesting complexes by allowing it to explore all potential pathways simultaneously. Similarly, certain bird species are believed to leverage quantum effects in their visual systems to sense the Earth's magnetic field, which aids in their navigation. However, quantum superposition also prompts numerous questions. Why do we not observe superposition in our daily lives? The answer may be attributed to a phenomenon known as decoherence. When a quantum system interacts with its environment, the superposition states become entangled with the numerous particles in that environment. This interaction effectively suppresses the superposition, rendering it unobservable in macroscopic systems. Decoherence elucidates why quantum behavior is generally restricted to microscopic scales and explains why Schrödinger's cat would not realistically be both alive and dead. The many worlds interpretation of quantum mechanics presents an alternative perspective, positing that every possible outcome of a quantum event occurs in a distinct branching universe. In the scenario of Schrödinger's cat, the cat exists alive in one universe and deceased in another. While this interpretation circumvents the necessity for wave function collapse, it presents a perplexing notion. An infinite array of parallel realities, each representing a distinct outcome of every quantum event. Quantum superposition also raises philosophical inquiries regarding the essence of reality. Is the quantum realm fundamentally probabilistic, or does it conceal a deterministic structure that remains undiscovered? The ongoing discourse between determinism and randomness carries significant implications for concepts such as free will, causality, and the very essence of existence. In the realm of cosmology, superposition provides valuable insights. It is believed that the early universe existed in a superposition of quantum states, with its development influenced by quantum fluctuations. These fluctuations have left traces in the cosmic microwave background radiation, which in turn has shaped the large-scale structure of the universe we observe today. Gaining an understanding of superposition in this context may yield clues about the universe's origins and the fundamental nature of space-time. The counterintuitive aspects of superposition also challenge our intuitions, prompting us to think beyond classical limitations. It encourages us to reevaluate the assumptions we often take for granted, such as the notion that objects possess definite properties, that time flows uniformly, and that reality exists independently of observation. By embracing the paradoxes inherent in superposition, we can attain a deeper comprehension of the universe's mysteries. Quantum superposition transcends being merely a scientific principle. It serves as a deep reminder of the intricacies of the universe and the constraints of human understanding. It unveils a realm in which particles can inhabit various states simultaneously, where observation influences reality, and where the distinctions between certainty and possibility become indistinct. This principle not only enhances our comprehension of quantum mechanics, but also fosters a sense of awe and curiosity regarding the essence of existence itself. General relativity. Imagine standing on a vast, flat plain. The ground stretches in all directions, and the sun rises high, providing light and warmth evenly. Now, picture someone setting a heavy object, like a massive boulder, in the middle of this plain. As the boulder settles, the surface begins to curve around it. The once flat ground bends and forms a dip, almost like a trampoline beneath it. This curvature of the ground is like the curvature of space and time described by Einstein's theory of general relativity, which redefined our understanding of gravity, space, and time. Before Einstein, gravity was understood through Sir Isaac Newton's theory. Newton saw gravity as a force that acted instantly at a distance, like a magnetic pull. If you dropped an apple, gravity would pull it toward the Earth instantly. This model worked well for everyday objects moving slowly compared to the speed of light. But when scientists observed stars, planets, and galaxies moving at near light speeds, Newton's model didn't work anymore. That's when Einstein changed everything with his theory of general relativity. Einstein proposed that gravity isn't a force but a distortion in space and time itself. Mass and energy bend and curve space-time around them, and this curvature dictates how objects move within it. Imagine space-time as a flexible, stretchy fabric. Mass and energy bend this fabric, and objects like planets and light follow the curves of space-time. To visualize this, think of a trampoline. If you stretch a large, heavy trampoline and place a ball in the center, the fabric will bend around it. If you roll a marble across the trampoline, it will follow the curve, moving toward the ball. Similarly, massive objects like the sun curve space-time, causing planets and light to follow curved paths. One famous prediction of general relativity is that massive objects like the sun can bend light that passes by them. This is called gravitational lensing. Imagine starlight traveling toward Earth. As it passes the sun, space-time curves, causing the light to bend. This effect has been observed many times, confirming Einstein's theory. The most dramatic consequence of general relativity is that gravity can bend space-time so much that it can bend light, alter time, and warp space itself. One of the most famous examples is black holes. A black hole forms when a star collapses, creating a gravitational field so strong that not even light can escape. According to general relativity, when a massive star runs out of fuel, it collapses into a point where space-time curves infinitely, creating a singularity. At this point, gravity becomes infinitely strong. Anything that crosses the event horizon, the point of no return, can't escape, not even light. The intense gravity bends light around the black hole, creating a visible boundary called the event horizon. Einstein predicted black holes long before they were observed. It wasn't until 2019 that scientists captured the first image of a black hole at the center of the galaxy M87. The image showed a dark circular shadow surrounded by glowing light, with a clear ring around the edge. This was the event horizon, and the light surrounding it was bent by the black hole's gravity, matching Einstein's predictions perfectly. Another important concept in general relativity is the interconnectedness of space and time. Space-time is not just the fabric of space, it's also how we understand time. For example, if you were traveling close to the speed of light in a spacecraft, time would pass differently for you compared to someone on Earth. According to general relativity, the faster you move, the slower time runs for you. This has been shown in experiments with fast-moving particles or highly accurate atomic clocks flown on jets. Time is relative, just as space is, and it stretches or contracts depending on your speed and the strength of gravity. This idea of time dilation has practical implications. If you were in a satellite orbiting Earth, time would move slightly faster for you compared to someone standing on Earth's surface. Without accounting for this difference, GPS systems would become less accurate over time. General relativity also predicts and explains gravitational waves. These are ripples in space-time caused by massive events like colliding black holes or neutron stars. The first detection of gravitational waves came in 2015, and since then, they've been used to study extreme cosmic events. General relativity changed our understanding of gravity, space, and time. It showed that these concepts are not fixed or separate, but interconnected and dynamic features of space-time itself. Space-time can bend, stretch, twist, and ripple depending on the presence of mass and energy. This flexibility leads to a new way of thinking about the universe, from black holes to cosmic expansion, time dilation, and gravitational waves. General relativity not only describes gravity, but reshapes how we understand the universe at its deepest level, opening a world of discovery and challenges that continue to expand human knowledge. Hawking radiation. Hawking radiation is one of the most groundbreaking and perplexing predictions in modern physics, offering insight into the strange nature of black holes and their connection to the quantum world. At first glance, the idea that black holes, known for trapping everything, including light, could actually emit radiation seems nonsensical. Yet this theory has become a cornerstone of theoretical physics, revealing the deep connection between quantum mechanics, general relativity, and the very nature of the universe. In 1974, British theoretical physicist Stephen Hawking proposed that black holes are not truly black, but instead emit radiation due to quantum effects near their event horizon, the boundary beyond which nothing can escape. This radiation, now known as Hawking radiation, emerges from the strange behavior of particles near the event horizon. To understand this, it helps to consider a basic concept from quantum mechanics, the vacuum. In classical physics, the vacuum is thought of as empty space, an absence of matter and energy. However, in quantum mechanics, the vacuum is never truly empty. It is filled with fleeting particles that appear and vanish in a fraction of a second, spontaneously popping into existence and annihilating each other. These virtual particles exist because of the uncertainty principle, which allows energy fluctuations even in what we perceive as empty space. Now, imagine this process occurring near the event horizon of a black hole. At this critical boundary, pairs of virtual particles, one positive and one negative, constantly appear and annihilate each other. However, when this happens near the event horizon, something extraordinary occurs. The intense gravitational field of the black hole can pull the virtual particles apart before they can annihilate each other. One particle falls into the black hole, while the other escapes into space. From an external perspective, it appears as though the black hole is emitting radiation. The escaping particle, with positive energy, can move away, while the particle that falls into the black hole carries negative energy, which reduces the black hole's mass. This is the essence of Hawking radiation particles emitted by the black hole due to quantum effects at the event horizon. Hawking's breakthrough was that this process could lead to the gradual loss of mass by the black hole, eventually causing it to shrink and potentially evaporate. If this radiation continues long enough, the black hole could lose enough mass to disappear entirely, leaving behind only the radiation. This concept of black hole evaporation challenges the traditional view of black holes as permanent cosmic features. It suggests that even the most massive black holes could eventually vanish. To fully grasp this idea, consider the conservation of energy. Normally, virtual particles appear in pairs, balancing out each other's energy. However, when one falls into the black hole, it carries negative energy, reducing the black hole's total mass. The escaping particle carries positive energy, which we observe as radiation. Over time, this process causes the black hole to lose mass, leading to its eventual evaporation. This idea has profound implications. It suggests that black holes may not be eternal, as once believed, and even the largest ones could eventually evaporate and disappear. Yet, despite its theoretical foundation, Hawking radiation has not been directly observed. The challenge of detecting it lies in its weak and faint nature, particularly for large black holes. The radiation emitted by a stellar mass black hole would be so faint that current technology cannot detect it. In contrast, tiny primordial black holes, which would have emitted stronger radiation, may have already evaporated, making them undetectable as well. Still, the theory of Hawking radiation is important because it raises fundamental questions about the nature of information and the laws of physics. One of the most intriguing aspects of black hole evaporation is its connection to the black hole information paradox, a puzzle that has baffled physicists for years. According to quantum mechanics, information about a system's state should never be lost. But if a black hole evaporates completely, what happens to the information that fell into it? the radiation emitted by the black hole appears random and devoid of any information about the objects that fell into it, seemingly violating the principle of information conservation. Some physicists believe that the resolution to this paradox lies in the nature of Hawking radiation itself. One possibility is that the information about the objects that fell into a black hole is not lost, but encoded in the radiation emitted by the black hole in a scrambled form. This idea, known as the soft hair theory, suggests that black holes may carry more information than previously thought, and that this information could be hidden within the correlations of the Hawking radiation. If this turns out to be true, it could resolve the information paradox and provide deeper insight into the relationship between quantum mechanics and gravity. Moreover, studying Hawking radiation provides insight into the fundamental structure of space-time and quantum gravity. The process of black hole evaporation might reveal new physics, offering a window into the unification of quantum mechanics and general relativity. This remains a major area of research as scientists attempt to reconcile gravity, which governs large objects, with quantum mechanics, which controls subatomic particles. Hawking radiation also has cosmological implications, particularly for the future of the universe. If black holes can evaporate, the universe may one day be devoid of them, leaving behind only their emitted radiation. Some theories suggest that the remnants of evaporated black holes might leave behind tiny Planck mass particles or other exotic objects, potentially playing a role in future cosmic evolution. While Hawking radiation has not been directly observed, it remains a powerful theoretical concept, reshaping our understanding of black holes, information, and the laws of the universe. It connects quantum mechanics, general relativity, and thermodynamics, offering a tantalizing glimpse into the mysterious processes governing the cosmos. As scientists continue to explore the secrets of black holes and space-time, Hawking radiation will undoubtedly remain central to understanding the universe's deepest mysteries. Quantum field theory. Imagine standing in the middle of a vast, empty field. The ground beneath you feels solid, yet in the world of quantum mechanics, this field is alive with invisible activity. It's not just any field, but a quantum field, the foundation of one of the most powerful ideas in modern physics, called quantum field theory, or QFT. At first, it might seem strange to think of empty space as full of energy, but in QFT, what seems like a vacuum is actually a lively, fluctuating space where particles constantly pop in and out of existence. In our daily lives, we usually think of particles as tiny solid things like marbles rolling around. QFT suggests something much deeper. Particles aren't individual objects, they are small disturbances in underlying fields that stretch across the universe. These fields are what truly make up reality, and what we see as particles, like electrons, photons, or quarks, are actually ripples or vibrations in these fields. To understand this better, think of the surface of a pond. If you throw a stone into the water, waves ripple outward from the point of impact. Similarly, a particle is like a ripple in a quantum field. The field doesn't go away when the ripple moves through it, just like water stays even after a wave passes. The big difference is that quantum ripples follow strange rules of quantum mechanics, not the usual rules of classical physics. Each fundamental particle comes from a specific quantum field. For example, electrons are ripples in the electron field, and photons are ripples in the electromagnetic field. These fields aren't located in one spot. They spread throughout space, and when we see a particle, we're just observing the effect of the field in one small area. Particles may look like separate things, but they're not. They're just excitations of the same continuous field. Another important part of QFT is how these fields interact. In classical physics, forces like gravity or magnetism are seen as invisible influences. In quantum field theory, these forces come from the exchange of virtual particles. These are particles that exist for a tiny moment and carry the force between two other particles. For example, when two electrons push away from each other, they're exchanging virtual photons. These photons can't be directly seen, but they explain how the force works. Virtual particles are central to many strange ideas in QFT. Imagine standing in a busy crowd where people are constantly passing by and brushing shoulders. You don't always see the interaction, but it's happening. That's how virtual particles behave in quantum fields. They constantly appear and disappear, briefly influencing the space around them before vanishing again. Even in a vacuum where it seems like nothing is happening, quantum fields continue to fluctuate. They create tiny bursts of energy that produce particle and antiparticle pairs. These appear out of nowhere, live for a brief instant, then cancel each other out. This is called vacuum polarization. It doesn't break the rules of physics because of Heisenberg's uncertainty principle, which says energy can be borrowed for a short time as long as it's returned quickly. This idea that empty space is still full of activity has led to real discoveries. One is the Casimir effect, where two metal plates placed very close in a vacuum are pulled toward each other. This pull isn't from any visible force, but from the energy of the fluctuating quantum fields between them. It proves that even in a perfect vacuum, space is never truly empty. QFT also describes the forces that control how particles behave. The electromagnetic force is carried by photons, the strong nuclear force by gluons, and the weak nuclear force by W and Z bosons. Gravity isn't yet fully included in QFT, but it's thought to be carried by a particle called the graviton. All of these forces in QFT are the result of interactions between quantum fields through the exchange of virtual particles. What makes QFT especially powerful is that it brings together two major parts of physics: quantum mechanics and special relativity. Quantum mechanics describes how particles behave at tiny scales, while relativity explains what happens at very high speeds. For years, physicists couldn't make these two theories work together, but QFT solved that problem by showing how quantum fields behave under both sets of rules. A major success of QFT is the Standard Model of Particle Physics, which describes how particles and forces work at the smallest scales. It explains how quarks, electrons, neutrinos, and other particles behave, and how they interact. It has been tested in huge experiments like those at the Large Hadron Collider. The discovery of the Higgs boson, which gives particles their mass, was a major proof of QFT's predictions. Even with all this success, QFT still leaves some questions. One of the biggest is how to include gravity. Right now, QFT can describe the other forces, but gravity remains separate. Scientists are working on theories like string theory and loop quantum gravity to bring everything together, but a complete answer hasn't been found yet. QFT also makes us think deeply about what space and matter really are. If particles are just ripples in fields, then what is space itself? Is it full of hidden fields we don't understand yet? These questions take us to the edge of current knowledge and show how much we still have to learn. In the end, QFT is a revolutionary idea that changed how we see the universe. It tells us that what we think of as solid individual particles are just brief excitations in invisible fields that stretch across all space. It helps us understand everything from the smallest particles to the forces that hold the universe together. And while we still don't have all the answers, QFT remains one of the most powerful and successful ideas in science. Black hole physics. Black hole physics explores a region in space where the known rules of the universe break down, a place where the forces of nature converge in such a way that they lose their usual meaning. At the heart of every black hole lies the singularity, a mysterious point where gravity is so intense that space-time itself becomes warped and distorted. This is where black hole physics takes shape, a field that challenges and expands our understanding of the universe's most extreme realms. While the concept of black holes dates back to the 18th century, it wasn't until Albert Einstein's general relativity theory in the early 20th century that we began to understand how these enigmatic objects form and behave. According to general relativity, when a massive object collapses under its own gravity, it can create a black hole, a region in space where gravity is so strong that not even light can escape. Once you pass the event horizon, the point of no return, escape is impossible. The physics of black holes is incredibly complex, but understanding them is vital for grasping the universe's deeper secrets. Black holes are places where space-time is stretched to its absolute limits, offering a perfect environment to test theories of gravity, quantum mechanics, and thermodynamics. In fact, black holes serve as one of the best laboratories for exploring the boundaries of our knowledge. The key to understanding these objects lies in the escape velocity, the speed at which an object must travel to overcome the gravitational pull of a massive body. While most objects in the universe have a relatively low escape velocity, as an object's mass grows denser, its escape velocity increases. For a black hole, this velocity reaches the speed of light itself, meaning that nothing, not even light, can escape. This is why black holes are invisible. They do not emit or reflect light, but reveal themselves through their interactions with nearby matter. The event horizon marks the boundary of a black hole, beyond which nothing can return. If you were to fall into a black hole, you would pass the event horizon and move toward the singularity at its center. As you descend, time itself would appear to slow down due to the extreme warping of space-time, and from an outside observer's perspective, you would seem to freeze in time at the event horizon. This brings us to a strange aspect of black holes: time dilation. As you approach a black hole, the gravitational field intensifies, causing time to slow down relative to someone observing from afar. However, from your perspective, time would continue normally, while an outside observer would see you gradually freeze in time. At the very center of the black hole lies the singularity, a point where gravity is infinitely strong, and space-time becomes infinitely curved. This is where the laws of physics break down, and no existing theory can fully explain the physics of such an extreme environment. The nature of the singularity remains one of physics' greatest mysteries. Despite these perplexing qualities, black holes also have another intriguing feature: they can be studied by observing the behavior of matter around them. Although we cannot directly observe the interior of a black hole, we can study the matter falling into it, often in the form of gas and dust, which forms an accretion disk. As this matter spirals inward, it heats up to extremely high temperatures, emitting X-rays and other radiation that can be detected from afar. Interestingly, black holes don't merely suck up matter like vacuum cleaners. Many are thought to play a crucial role in shaping galaxies and the broader universe. As matter falls into a black hole, it can release enormous amounts of energy that affect the surrounding space. For example, the supermassive black hole at the center of our Milky Way is believed to power some of the most energetic phenomena in the universe, such as quasars, bright, distant objects that emit vast amounts of radiation. Black holes also offer insights into one of modern physics' most pressing questions: how to unify general relativity and quantum mechanics. General relativity explains the behavior of massive objects and space-time's curvature, while quantum mechanics deals with subatomic particles. These theories, though highly successful in their respective domains, seem to contradict one another under extreme conditions like those found at the singularity, where both gravity and quantum effects are most pronounced. Understanding black holes might help unlock a theory of quantum gravity, a major goal in physics. In 1974, Stephen Hawking made a revolutionary discovery regarding black holes' thermodynamics. He proposed that black holes are not entirely black, but emit radiation, now known as Hawking radiation. According to quantum mechanics, empty space isn't truly empty, but teems with virtual particles that constantly appear and disappear. Near the event horizon, these particles can split, with one falling into the black hole and the other escaping. The escaping particle is detected as radiation, which gradually causes the black hole to lose mass and energy. Over incredibly long periods, this could lead to a black hole's eventual evaporation. Hawking's discovery was groundbreaking because it suggested that black holes might not be permanent and could eventually die by radiating away their mass. This raised further questions about the nature of information in the universe. If a black hole evaporates completely, what happens to the information inside it? This is the black hole information paradox, one of the most debated issues in theoretical physics. Solving this paradox could have profound implications for our understanding of quantum mechanics and the nature of reality. Despite these breakthroughs, many mysteries remain. For example, we still don't fully understand what happens at the singularity or how to reconcile quantum mechanics and general relativity in black holes. However, one thing is certain. Black holes are some of the most fascinating and enigmatic objects in the universe. They challenge our deepest assumptions about space-time and the cosmos, and studying them will continue to push the limits of human knowledge for years to come. Observer effect. The observer effect is a captivating and complex phenomenon within quantum physics that evokes both intrigue and confusion. This concept posits that the mere act of observing an object can alter its behavior. At first, this notion may appear illogical. How can something as passive as looking at an object influence its characteristics? The explanation lies in the peculiar and counterintuitive principles of quantum mechanics, where observation does not merely document a system's state, but actively contributes to its formation. To illustrate this, consider a common scenario, measuring the temperature of a cup of coffee. You insert a thermometer into the coffee and read the temperature, assuming the thermometer simply records the coffee's temperature without affecting it significantly. This assumption reflects how we typically perceive measurements, gathering information without causing any change. However, in the quantum realm, the situation is far more complex. The act of measurement can profoundly disturb the system being observed. Central to the observer effect is the principle of superposition in quantum mechanics. Particles do not possess definite properties until they are observed. Instead, they exist in a superposition, representing a combination of all potential states. For instance, consider an electron within an atom. Unlike classical physics, where it would follow a predictable trajectory, the electron exists in a cloud of probabilities, potentially occupying multiple locations simultaneously, each with varying speeds, spins, and energies. It is only when we measure its position or momentum that this cloud of possibilities collapses into a single, definitive outcome. Thus, the observer effect implies that our understanding of a system is not the only aspect that changes upon measurement. The observer effect is most famously illustrated by the double-slit experiment, a fundamental concept in quantum physics. Picture a barrier with two slits and a detection screen positioned behind it to register where particles, such as electrons, land. When electrons are directed at the slits without measuring which one they pass through, they exhibit wave-like behavior, resulting in an interference pattern on the screen, as if each electron is simultaneously traversing both slits. However, once a detector is placed at the slits to ascertain the path of the electrons, the interference pattern vanishes, and the electrons revert to behaving like particles, landing in distinct locations. This phenomenon indicates that the mere act of measuring or observing the electron's trajectory alters its behavior. This leads to a profound philosophical inquiry. If observation influences a particle's behavior, what implications does this have for the nature of reality? Some physicists and philosophers propose that the universe lacks definitive properties until it is observed. This notion starkly contrasts with our daily experiences, where objects such as cars or trees appear to exist independently of our observation. In the quantum realm, however, particles seem to exist in a state of potentiality, enveloped in a cloud of probabilities until they are observed. Consequently, the observer effect prompts us to reconsider our understanding of reality. Does the universe exist solely as a collection of possibilities awaiting realization through conscious observation? A notable quote related to the observer effect comes from physicist Niels Bohr, who stated, "Everything we call real is made of things that cannot be regarded as real." In this context, Bohr highlighted the peculiar probabilistic nature of reality at the quantum level. Our everyday understanding leads us to assume that objects possess fixed properties. An apple is consistently red, and a chair invariably has 4 legs. However, quantum mechanics reveals that at the subatomic level, reality is significantly more fluid and uncertain. This raises practical questions. If observation can alter the state of a system, what implications does this have for the observer's role in the universe? One theory that has emerged is the concept of a participatory universe, proposed by physicist John Archibald Wheeler. Wheeler posited that the universe is, in some respects, contingent upon the observer. He argued that the universe is not a static, pre-existing entity, but is actively shaped through the act of observation. This does not imply that the universe ceases to exist when unobserved. Rather, it suggests that its properties may be influenced by our perceptions. Wheeler's participatory universe is closely linked to the idea that consciousness plays a crucial role in shaping reality. Although this notion remains contentious, it has garnered interest in both physics and philosophy, particularly in discussions surrounding quantum mechanics and consciousness. Some theorists propose that consciousness is fundamental to the physical realm, asserting that our observations of quantum systems are not merely passive measurements, but rather contribute to the co-creation of the quantum world we perceive. However, not all scientists concur with this interpretation. Many argue that the observer effect is simply a consequence of the limitations of our measurement tools. From this perspective, the effect does not suggest that consciousness influences particles, but rather that our measurement attempts inevitably disturb quantum systems. In the double-slit experiment, the act of placing a detector at the slits does not necessitate human observation. Rather, it is the interaction between the measuring device and the particles that induces a change. In this context, the observer effect may not pertain to consciousness, but rather to the unavoidable disturbance that arises from any form of measurement. While discussions on this topic persist, the observer effect carries significant implications for our comprehension of the quantum realm and the essence of reality. It reveals that at the quantum level, the distinction between the observer and the observed is far more ambiguous than one might anticipate. This is not merely a technical detail, it represents a fundamental transformation in our understanding of existence within a universe governed by quantum mechanics. The act of observation itself can modify the observed entity, challenging our foundational beliefs regarding the separation of subject and object, as well as the perceiver and the perceived. Moreover, the observer effect has practical applications in contemporary technology. One of the most promising areas to arise from quantum mechanics is quantum computing. Quantum computers leverage the principles of quantum mechanics, such as superposition and entanglement, to execute calculations with far greater efficiency than traditional computers. However, the observer effect is also critical in this domain. To obtain meaningful information from a quantum system, measurement is necessary, yet this measurement inevitably disturbs the system, collapsing its superposition into a definitive state. This presents a challenge for quantum computing, as it necessitates meticulous management of quantum states while minimizing the disturbances caused by measurement. Similarly, quantum cryptography is founded on the principles of quantum mechanics, including the observer effect. One of the fundamental aspects of quantum cryptography is its exceptional security. Any attempt to eavesdrop on the system disrupts the quantum states being transmitted, thereby notifying both parties of an intruder's presence. In this context, the observer effect is a beneficial characteristic of quantum information systems, offering a level of security that surpasses that of classical encryption methods. Consequently, the observer effect transcends mere philosophical inquiry. It has practical implications that influence various fields, from the design of quantum computers to the advancement of secure communication technologies. This phenomenon challenges our comprehension of the universe and compels us to acknowledge the profound interconnectedness between the observer and the observed. Whether we are investigating the essence of consciousness, the nature of reality, or the boundaries of our technological advancements, the observer effect serves as a poignant reminder that the universe is more complex than we often perceive. In the realm of quantum mechanics, nothing is as straightforward as it appears, and even our most basic acts of observation can alter the very fabric of reality. Quantum entanglement. Quantum entanglement stands as one of the most perplexing concepts in contemporary physics, often appearing to contradict logic and common sense. Consider a pair of particles, such as two electrons, that are generated in a manner that links their properties, irrespective of the distance separating them. Once entangled, these particles exchange information in ways that seem impossible according to classical physics. It is as if the state of one particle instantaneously affects the state of the other, regardless of how far apart they are. To grasp this unusual phenomenon, we must delve into the realm of quantum mechanics. In this domain, particles do not function as solid, well-defined entities. Rather, they exist in a state of probability, with their properties becoming definite only upon measurement. This sharply contrasts with our everyday experiences, where objects like chairs, cars, and people exhibit predictable and stable characteristics. In the quantum world, however, entities are in a constant state of flux, existing in multiple states at once until observed. This concept is known as superposition and is a fundamental principle of quantum mechanics. Now, let us explore further. Imagine two entangled electrons. Prior to measurement, both electrons exist in a superposition of various potential states. When one electron is measured, let's say its spin, a fundamental property of particles, the state of the second electron is instantaneously determined, regardless of the distance between them. This phenomenon suggests that the two particles are interconnected, sharing information instantaneously. Even if one is located on Earth and the other is located on Mars, other is light years away in a distant galaxy. This encapsulates the essence of quantum entanglement. The situation becomes even more fascinating when considering Albert Einstein, who famously described this phenomenon as spooky action at a distance. He found it profoundly unsettling because, according to the theory of relativity, no information can exceed the speed of light. However, quantum entanglement appears to imply that information between entangled particles is exchanged instantaneously, thereby contradicting the constraints established by relativity. Einstein's skepticism was shared by Niels Bohr, a prominent figure in the advancement of quantum mechanics who was deeply engaged in investigating the ramifications of entanglement. Nevertheless, decades of experimental research have validated the existence of entanglement, leaving physicists perplexed. In the 1960s, physicist John Bell formulated a theorem, known as Bell's theorem, which demonstrated that the predictions of quantum mechanics regarding entanglement could be empirically tested. This theorem indicated that if quantum mechanics were accurate, entangled particles would breach certain inequalities that were believed to be valid in classical physics. Numerous experiments, including those conducted by physicists like Alan Aspect in the 1980s, have consistently corroborated the predictions of quantum mechanics, showing that entangled particles indeed violate these classical inequalities. Thus, the peculiar nature of entanglement is not merely a theoretical notion. It has been substantiated by empirical evidence. But what implications does this have? Why do entangled particles exhibit such behavior, and how can we comprehend it? One potential explanation is that quantum entanglement may not be about particles communicating over great distances, but rather about a profound connection that transcends both space and time. Instead of perceiving particles as isolated entities, we might consider them as components of a unified whole, existing within a broader quantum system. This viewpoint challenges the conventional ideas of separateness and individuality that characterize classical physics, urging us to rethink the universe in more interconnected terms. Arrow of time. The concept of the arrow of time serves as the fundamental thread that interlaces our universe. However, its unidirectional flow remains one of the most perplexing elements of reality. Beyond the realms of entropy and thermodynamics, the arrow of time prompts us to explore significant inquiries. Is time merely an illusion? Is it possible for time to reverse? Furthermore, how does it influence not only the physical realm, but also our memories, choices, and the way we derive meaning? The arrow of time transcends the boundaries of physics. It dictates our experience of existence. Our perception of time is intricately linked to our capacity to create memories. When we recall past events, our brains encode and retrieve specific patterns of neural activity, which represent those experiences. This memory process contributes to an increase in entropy, both within the brain and the surrounding environment, in accordance with the second law of thermodynamics. Additionally, we do not have memories of the future because memory relies on patterns of cause and effect that unfold in the direction of the arrow of time. Interestingly, neuroscientific research indicates that the brain may utilize entropy when making decisions or planning for the future, simulating various potential outcomes and exploring higher entropy states to navigate uncertainty. This capability to envision the future while remaining anchored in an irreversible past provides humans with a sense of temporal directionality. In the realm of quantum mechanics, however, the arrow of time becomes less clear-cut, as the fundamental equations governing quantum phenomena exhibit time symmetry, functioning equally well in both forward and backward directions. Recent studies on quantum entanglement and decoherence offer insights into the behavior of particles during interactions. When particles engage with one another, their quantum states become intertwined, leading to the evolution of their combined wave functions within a system characterized by numerous particle interactions. Over time, interactions with the environment result in a degradation of quantum coherence, a phenomenon known as decoherence. This shift from a quantum state to a classical state gives rise to an emergent arrow of time. While individual particles do not perceive time directionally, the systems they create manifest a macroscopic reality that reflects the forward progression of time, stemming from their collective behavior. In this perspective, the arrow of time may not be an intrinsic feature, but rather a consequence of complex systems arising from the quantum chaos of the microscopic realm. If we liken time to a river, black holes can be seen as whirlpools, regions where the fabric of space-time is warped and distorted. Near a black hole's event horizon, time experiences a significant slowdown due to intense gravitational forces. From an external viewpoint, objects approaching a black hole seem to be frozen in time, their descent appearing infinitely delayed. However, black holes do more than merely stretch time. They also absorb information and contribute to an increase in entropy. The relationship between these phenomena is fundamental to contemporary physics. For example, Hawking radiation enables black holes to emit energy and gradually diminish in size, yet this introduces a paradox. What becomes of the information that has fallen into the black hole? The black hole information paradox implies a deep connection between time, entropy, and the underlying structure of the universe. One intriguing hypothesis suggests that black holes might function as cosmic time capsules, preserving the arrow of time within their event horizons. As they evaporate, they could potentially release this information back into the universe, possibly resetting entropy in ways that remain beyond our current comprehension. Could the arrow of time ever reverse? Some cosmological theories propose that in a cyclic universe, where expansion is succeeded by contraction, time might flow backward during the contraction phase. In such a scenario, entropy would decrease, and the arrow of time would invert. This notion introduces intriguing possibilities. Could memories be unmade, stars reignite, and shattered glass reassemble? In speculative multiverse models, time may behave differently across various universes. It is conceivable that entropy could increase and then decrease in a cyclical manner, creating regions of reversed time. Although these concepts remain unproven, they prompt us to reconsider time not as a universal constant, but as a property influenced by context and conditions. Beyond its significance in physics, time is essential in how we organize and comprehend our surroundings. We rely on calendars, clocks, and measurements to structure our lives. Ideas such as progress, growth, and legacy, central to human civilization, are intrinsically linked to the directionality of time. Without the forward flow of time, we would lack a sense of history or the ability to plan for the future. From a scientific perspective, the direction of time is vital for understanding cause and effect. If time were to reverse, the natural order of events would collapse, making it impossible to predict outcomes. The arrow of time guarantees that each event follows the previous one in an irreversible sequence, meaning that the patterns of the past can never be replicated exactly in the future. While the ultimate trajectory of time may lead to the universe's heat death, where energy becomes uniformly distributed and processes cease, it is this very progression that enables complexity, life, and the formation of structures within the universe. The relentless advance of time fuels the processes that power stars, sustain biological evolution, and allow civilizations to rise and fall. The progression of time is what enables the universe to experience dynamic change and evolution, ranging from the tiniest quantum particles to the most significant cosmological phenomena. The arrow of time serves as the connecting thread among all these elements. Time is not merely a dimension in which events occur. Rather, it constitutes the framework within which the history of the universe is recorded, with entropy acting as the guiding mechanism for its progression. String theory. String theory stands as one of the most ambitious concepts in modern physics, yet it remains a deeply enigmatic and widely debated theory. Its intrigue lies in its attempt to address one of the most profound questions: how does everything in the universe, every particle, force, and interaction, fit together into a single, unified framework? Humanity's quest to comprehend the fundamental nature of the universe has been long, with philosophers, scientists, and thinkers grappling with the question of what the universe is made of and how it operates at the most basic level. In the 20th century, we uncovered many secrets of the universe through quantum mechanics and general relativity, but these two frameworks have never fully aligned. String theory boldly seeks to resolve this discrepancy, aiming to reconcile the quantum world of subatomic particles with the vast expanse of spacetime described by general relativity. Imagine trying to assemble a perfect picture of the universe with two jigsaw puzzles. One puzzle represents the quantum world of particles, where the laws of physics are strange and counterintuitive. The other puzzle describes the cosmos, from planets and stars to the very fabric of spacetime. The problem is that the pieces from both puzzles don't seem to fit together. One puzzle is based on discrete, probabilistic interactions of particles, while the other relies on the smooth, continuous structure of the universe. String theory suggests that the solution to this problem lies in looking at the smallest building blocks, tiny, vibrating strings that make up everything. String theory's journey began in the 1960 seconds, when physicists sought to understand the behavior of subatomic particles. At that time, particle physics was a rapidly advancing field, with new particles being discovered almost annually. These particles were thought to be point-like objects, meaning they had no internal structure, existing simply as points in space. However, as physicists probed further, they found that the equations describing these point particles didn't make sense at extreme conditions, predicting infinite energies or unphysical results. This pointed to the need for a deeper, more fundamental description, leading to the birth of string theory. The concept arose from studying the strong nuclear force, responsible for holding atomic nuclei together. The equations describing the strong force seemed similar to the mathematics used to describe the vibrations of strings, sparking an intriguing observation. In string theory, the fundamental objects are not point particles but tiny, vibrating strings. Much like how a guitar string vibrates in different patterns, strings in string theory vibrate in various ways. These vibrations correspond to different particles, such as electrons and quarks. The theory proposes that all particles and forces in nature are manifestations of these vibrating strings. This is a radical shift from the classical view of particles, which were once thought of as individual points. Instead, string theory imagines particles as one-dimensional strings that can stretch and vibrate in different ways, determining their properties like mass, charge, and other characteristics. This theory suggests that all fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, are simply different aspects of the same underlying reality. One of the most mind-boggling elements of string theory is its suggestion that the universe consists of more than the three spatial dimensions we experience. String theory posits that additional dimensions exist, curled up so small that we can't detect them directly. In the simplest version of string theory, there are 10 dimensions, 9 spatial and 1 temporal. These dimensions are compactified at scales too tiny to observe, potentially as small as the Planck length, which is around 10⁻35 meters. To put that in perspective, if a string were the size of a tree, these extra dimensions would be smaller than subatomic particles. While we can't directly observe these dimensions, string theory suggests they exist and profoundly influence the universe's physics. Imagine a garden hose at a distance. It appears to be a one-dimensional object, but a closer look reveals that it has a circular cross-section. In the same way, string theory suggests that extra dimensions are curled up in ways we can't perceive, but that affect the behavior of particles and forces. These extra dimensions allow string theory to unify all the fundamental forces of nature. In our three-dimensional world, we see gravity, electromagnetism, and the nuclear forces as separate. But in the multidimensional world of string theory, they are seen as different expressions of the same force. Another important aspect of string theory is supersymmetry, which proposes a theoretical symmetry between two types of particles, bosons and fermions. Bosons are force carriers, like photons, which mediate electromagnetism, and gluons, which mediate the strong force. Fermions are the building blocks of matter, such as electrons and protons. Supersymmetry suggests that for each particle there exists a superpartner with different spin characteristics. For example, the photon would have a superpartner called the photino, and the electron would have a superpartner called the selectron. Supersymmetry would effectively double the number of particles in the standard model of particle physics. Although supersymmetry remains unproven experimentally, it plays a key role in making string theory mathematically consistent and unifying the forces of nature. One of string theory's most compelling aspects is its potential to integrate gravity into the quantum realm. For decades, gravity and quantum mechanics have remained incompatible. Quantum mechanics governs the behavior of particles at tiny scales, while gravity, as described by general relativity, governs the large-scale structure of the universe. String theory offers a potential bridge between these two, with gravity mediated by a particle called the graviton. This particle is associated with the vibrations of strings, just as other particles like photons emerge from different vibrational modes. In this way, string theory could describe gravity alongside electromagnetism and nuclear forces, offering a potential path to quantizing gravity. Despite its elegant mathematical structure, string theory remains speculative, as no direct experimental evidence has been found to support it. The energy scales relevant to string theory are far beyond the reach of current particle accelerators. The smallest scales of string theory are the Planck scales, many orders of magnitude smaller than what current technology can probe. However, scientists remain hopeful that advancements in particle accelerators, like the Large Hadron Collider, may eventually provide indirect evidence. If supersymmetry is correct, we might detect supersymmetric particles. String theory also makes predictions about black holes and the quantum structure of space-time, which could be tested with cosmic observations. For now, string theory continues to be a vibrant area of theoretical research. It has already provided deep insights into the nature of space, time, and the fundamental forces. Whether or not it will eventually be confirmed by experiment is uncertain, but its elegance and potential to answer some of the deepest questions in physics make it one of the most fascinating concepts in modern science. String theory presents a vision of the universe that unites all forces and particles into a single, cohesive framework, offering hope that the mysteries of the cosmos might one day be unlocked through the vibrations of tiny strings.
Quantum tunneling. Quantum tunneling is one of the most fascinating and mind-bending ideas in quantum physics. It goes completely against how we experience the world in everyday life. Imagine a ball rolling toward a hill. In classical physics, if the ball doesn't have enough energy to reach the top, it won't make it over. It either rolls back down or just stops at the base of the hill. But in the quantum world, things work very differently. The ball doesn't need to go over the hill sometimes, it can simply pass through it, appearing on the other side as if the hill wasn't even there. That's the strange idea behind quantum tunneling. Particles that should be blocked by a wall or barrier can, with some probability, go right through it. And this is just the beginning of what makes tunneling so fascinating. At first, tunneling seems to break the rules of classical physics, and yet, it's a core part of quantum mechanics that scientists have confirmed in many experiments. But how can a particle pass through something it doesn't have enough energy to get over? To answer that, we need to explore the strange world of quantum mechanics, a world where particles don't have exact positions or paths unless we measure them. Instead, they exist as probabilities, like waves of possibilities spread out across space, rather than being fixed points. It's this wave-like behavior that makes quantum tunneling possible. Imagine an electron. It doesn't exist in just one spot. Instead, it's like a cloud of chances, a spread-out possibility of where it might be. In quantum mechanics, this is described using a mathematical tool called a wave function, which tells us the likelihood of where we'll find the particle if we look for it. Now imagine this electron approaching a barrier. The wave function doesn't stop at the wall, it fades, but it continues through. That means there's a chance, even if it's small, that the electron could appear on the other side of the barrier, even without having enough energy to cross it. Think of a person standing in front of a wall. In the everyday world, if they don't have the energy to climb or jump over it, they simply stay put. But in the quantum world, that person's wave function would extend past the wall. There's a tiny chance they could appear on the other side as if they magically passed through. This behavior is nothing like what we see in daily life, where objects follow the predictable rules of classical physics. In the quantum world, particles can be in multiple possible places at once, and some of those possibilities include going through walls. The chance that a particle will tunnel through something depends on a few things: how wide and tall the barrier is, how much energy the particle has, and what its wave function looks like. The harder it is to get through the wall, the less likely tunneling becomes. But it's never completely impossible. This chance is described by the Schrödinger equation, the math that explains how wave functions behave and change over time. What makes tunneling even more amazing is that it isn't just a theory, it actually plays a big role in how the world works. One major example is nuclear fusion in stars. The sun and other stars shine because hydrogen atoms fuse together to form helium, releasing huge amounts of energy. But hydrogen atoms, specifically protons, are all positively charged, so they naturally repel each other. In classical physics, they shouldn't have enough energy to overcome that repulsion and fuse. But thanks to quantum tunneling, they don't need to crash into each other head-on, they can tunnel through the barrier and fuse anyway. Without this, stars couldn't shine, and life on Earth wouldn't exist. Tunneling also helps in technology. Take the scanning tunneling microscope, which lets scientists see individual atoms. It works because electrons can tunnel through barriers, and the device measures the current created when that happens. That current shows the shape of surfaces at the atomic level. Without tunneling, this kind of microscope wouldn't work, and we'd be limited in what we could learn about tiny materials. Tunneling is also used in electronics, like in tunnel diodes and quantum dots, which are found in many modern computing and electronic devices. Even though it's so important, quantum tunneling is still hard to fully understand. It raises big questions about the nature of reality. If particles can pass through barriers, does that mean the universe is unpredictable? Are particles constantly moving between different realities? Some versions of quantum theory say that tunneling is part of the many worlds interpretation, where every possible outcome happens in its own universe. In that view, tunneling doesn't break any rules. It's just us seeing one version of an event that exists in many forms across parallel worlds.
This idea is still speculative, but it adds to the mystery of quantum tunneling. Another key part of tunneling is the barrier height and thickness. In general, the thicker and taller the barrier, the less likely a particle will tunnel through. But no matter how high or wide, there's always a small chance. This randomness shows how the quantum world runs on probability, not certainty. In classical physics, things have exact positions, speeds, and directions. But in the quantum world, particles exist in a cloud of potential until they are measured. Once we observe them, they settle into a definite state. Until then, they're just waves of possibility. This unpredictability is at the heart of quantum mechanics. It goes against what we're used to in our everyday experiences. At a normal scale, things need a certain amount of energy to overcome obstacles. But at the quantum level, particles follow different rules, and those rules can lead to surprising outcomes like tunneling. It's a strong reminder that our usual way of thinking doesn't always apply to the microscopic world. In that strange realm, physics takes on a whole new form. To sum it all up, quantum tunneling is one of the strangest but most important parts of quantum physics. It shows that particles can get past barriers they shouldn't be able to cross. This idea isn't just theoretical, it powers the fusion in stars and helps us build tools like high-tech microscopes. Tunneling teaches us that the quantum world works in ways very different from what we're used to. It's all about probabilities, uncertainty, and rules that are far removed from our daily experience. As we keep exploring the quantum realm, tunneling reminds us how much there still is to learn about the deepest layers of the universe. Entropy is a fundamental yet often misinterpreted concept in physics, influencing everything from cosmic behavior to everyday occurrences. When asked to define it, many people resort to vague terms like disorder or chaos. However, entropy encompasses much more. It relates to energy, information, and the irreversible progression of time itself. To illustrate this, consider a thought experiment involving a pristine sandcastle on a beach, with its grains carefully arranged into towers and arches. When the tide comes in, it washes the sandcastle away, scattering the grains randomly across the shore and merging them with countless others. The sandcastle disappears, replaced by randomness. This transition from order to a state of increased randomness encapsulates the essence of entropy. Yet, entropy is not merely about chaos. It pertains to the number of potential configurations a system can adopt. While the sandcastle has a specific arrangement, the scattered grains can form countless different configurations. The greater the number of possible arrangements, the higher the entropy. In the 19th century, physicist Ludwig Boltzmann formalized the concept of entropy, demonstrating that it quantifies the number of microscopic configurations that correspond to a system's macroscopic state. Ludwig Boltzmann established the concept of entropy, demonstrating that it quantifies the number of microscopic arrangements that correspond to a system's macroscopic state. For instance, a container of gas can exhibit an infinite variety of molecular configurations while still maintaining the same temperature and pressure. Similarly, a shuffled deck of cards possesses significantly more possible arrangements than a perfectly ordered one, resulting in a higher entropy for the shuffled state. This understanding leads us to the second law of thermodynamics, a fundamental principle in science, which asserts that in an isolated system, entropy will either remain constant or increase over time. This principle elucidates why hot coffee cools rather than warms. Heat energy disperses into the surrounding air, thereby increasing the system's entropy. The second law indicates that processes tend to progress toward states of higher entropy as these configurations are statistically more likely. Entropy is not solely a measure of disorder. It is a driving force behind processes that shape our universe. For example, nuclear fusion in the sun transforms hydrogen into helium, releasing energy that radiates into space. This energy dispersal contributes to an increase in entropy and is essential for sustaining life on Earth by providing sunlight for photosynthesis. Without this ongoing rise in entropy, life as we know it would not be possible. A prevalent misunderstanding is to equate entropy exclusively with chaos. While higher entropy may appear more disordered, it fundamentally pertains to the distribution of energy and probabilities. For example, a broken glass on the floor exhibits greater entropy than an unbroken one, as there are significantly more configurations for its fragments to be scattered than for it to remain intact. Entropy also delineates the direction of time. Observing a glass shatter clearly indicates whether time is progressing forward or reversing, as entropy consistently increases in one direction. Although the laws of physics are time-symmetric and do not inherently differentiate between past and future, entropy introduces the irreversible progression of time that we perceive. Entropy also impacts our daily activities. For instance, making a bed or washing dishes decreases local entropy by establishing order. However, these actions require energy, which in turn raises entropy in other areas. Cooking breakfast or cleaning involves energy consumption that dissipates as heat, thereby contributing to the overall entropy of the system. Furthermore, entropy imposes limitations on the efficiency of technology, such as engines. Not all heat produced can be transformed into useful work, as some energy inevitably disperses, leading to an increase in entropy. This fundamental constraint explains why no machine can achieve 100% efficiency. Living organisms may appear to challenge the concept of entropy due to their ability to form intricate, ordered systems. However, they achieve this by exchanging energy and matter with their environment. For instance, humans consume food to establish and maintain order within their bodies, while simultaneously releasing heat and waste into the surroundings, which contributes to an increase in entropy. Life does not contravene the second law of thermodynamics. Rather, it functions within its parameters. Even the process of creativity is intertwined with entropy. When addressing problems, our minds navigate through various configurations of ideas before reaching a solution, similar to how systems naturally explore states of higher probability. The relationship between entropy and information theory is significant. Claude Shannon illustrated that randomness and information are mathematically interconnected. For example, a book written in an unfamiliar language may seem like a collection of random symbols representing high entropy, but to someone fluent in that language, it is rich with meaning. Data compression techniques aim to minimize redundancy and reduce entropy, further emphasizing this relationship. Ralph Landau's discovery in the 1960s showed that erasing information leads to an increase in entropy, establishing a direct correlation between computation and the second law. Deleting a file, for instance, generates a small amount of heat, demonstrating that even digital actions adhere to thermodynamic principles. The universe originated from an exceptionally low entropy state during the Big Bang, and over billions of years, entropy has gradually increased, influencing the formation of stars, galaxies, and life itself. This initial low entropy condition accounts for the arrow of time and the irreversible evolution of the universe. The reasons behind this initial state remain one of the great enigmas in physics, with theories ranging from statistical anomalies to multiverse concepts. Black holes serve as a prime illustration of entropy on a cosmic scale. Jacob Bekenstein and Stephen Hawking revealed that the entropy of black holes is directly related to the area of their event horizon. This entropy is extraordinarily high, far surpassing that of the stars from which they originated. Black holes emit Hawking radiation, gradually losing mass and contributing to the increase of entropy in the surrounding universe, ultimately leading to their complete evaporation. The notion of black hole entropy has sparked significant advancements in our understanding of space-time, quantum mechanics, and the holographic principle, which posits that the universe's informational content may be encoded on a two-dimensional surface. If the second law of thermodynamics is upheld, the universe will eventually attain maximum entropy, a condition referred to as heat death. In this scenario, energy will be uniformly distributed, rendering any meaningful work impossible. Stars will extinguish, galaxies will drift apart, and even black holes will dissipate, resulting in a cold, dark cosmos. While this perspective may be disheartening, it highlights the rarity and beauty of our present moment, a universe rich in complexity and life. Entropy transcends a mere physical concept. It provides a framework for comprehending the universe, existence, and the passage of time. By examining its relationships with information, computation, and cosmology, we recognize a world influenced by probability and energy distribution. Entropy serves as a reminder of the transience of all things, while simultaneously celebrating the ephemeral complexity and creativity that arise throughout existence. Although disorder may be unavoidable, it is within this context that life and meaning flourish. Wave-particle duality. Wave-particle duality stands as one of the most intriguing and paradoxical concepts in physics, challenging our traditional perceptions of the universe. Consider light streaming through your window on a bright day. To the unaided eye, it appears to be a continuous and smooth entity, filling your space with warmth. However, upon closer examination, one uncovers a remarkable reality. Light exhibits characteristics of both a wave and a particle, contingent upon the method of observation. This duality, both simple and profound, serves as a fundamental principle of quantum mechanics and has transformed our understanding of reality. To comprehend wave-particle duality, it is beneficial to explore the historical context that led to its revelation. For centuries, scientists engaged in a debate over whether light was a wave or a particle. In the 17th century, Isaac Newton advocated for the particle theory of light, or corpuscular theory, which accounted for phenomena such as reflection and refraction. Concurrently, Dutch physicist Christian Huygens proposed that light functioned as a wave, highlighting its capacity to bend around obstacles and exhibit interference patterns. These two perspectives appeared irreconcilable, each backed by experimental findings, yet unable to fully elucidate the diverse behaviors of light. The wave theory gained considerable traction in the early 19th century, particularly following Thomas Young's renowned double-slit experiment. Young conducted an experiment by directing light through two narrow slits onto a screen, where he observed an interference pattern characterized by alternating bright and dark fringes. This phenomenon indicated that light waves were overlapping and interfering with one another, presenting a challenge to the notion of light as merely a stream of particles. The wave theory of light appeared to be validated, leading to a temporary resolution of the debate. However, the onset of the 20th century disrupted this apparent agreement. In 1905, Albert Einstein published a revolutionary paper on the photoelectric effect, demonstrating that light could dislodge electrons from a metal surface. Importantly, the energy of these emitted electrons was determined not by the intensity of the light, but by its frequency. To elucidate this, Einstein proposed that light consists of discrete energy packets known as photons, with each photon carrying energy proportional to its frequency, expressed mathematically as E equals hf, where h represents Planck's constant and f denotes the frequency of light. This particle-like behavior of light revived the notion that it possessed both wave and particle characteristics. Einstein's contributions earned him the Nobel Prize in 1921 and compelled scientists to confront the complex reality that light could exhibit both wave-like and particle-like properties depending on the circumstances. The narrative did not conclude with light. As quantum mechanics evolved, Researchers found that electrons, once regarded solely as particles, could also demonstrate wave-like behavior. This revelation expanded the concept of wave-particle duality beyond light to include all matter, a principle formalized in Louis de Broglie's hypothesis. De Broglie proposed that particles such as electrons have an associated wavelength that is inversely proportional to their momentum. This idea was experimentally validated in 1927 when Clinton Davison and Lester Germer demonstrated electron diffraction by passing electrons through a crystal lattice. The interference pattern observed in this experiment reflects the behavior of light as demonstrated in Young's double-slit experiment, indicating that matter can also exhibit wave-like properties. To illustrate this duality, consider the ripples created in a pond when a stone is thrown. These ripples exemplify wave behavior, characterized by attributes such as wavelength and frequency. In contrast, the stone itself represents a localized object with a specific position and momentum similar to a particle. Wave-particle duality posits that quantum entities, such as photons and electrons, embody both wave-like and particle-like characteristics, but never simultaneously during observation. This leads us to the essential role of measurement in quantum mechanics. When we observe a particle, its wave-like nature appears to collapse, resulting in its manifestation as a particle at a defined location. However, when not observed, it exists as a wave of probabilities, mathematically representing all potential outcomes. This duality is not a limitation of our measurement tools or understanding. Rather, it is a fundamental aspect of reality. The concept of wave-particle duality becomes even more intriguing in the context of modern double-slit experiments conducted with individual particles, such as electrons. When electrons are fired one at a time through two slits, an interference pattern gradually forms, suggesting that each electron behaves as a wave and interferes with itself. However, if detectors are placed at the slits to ascertain which slit an electron traverses, the interference pattern vanishes and the electrons behave like particles. This phenomenon highlights the observer's influence on reality and raises significant philosophical inquiries regarding the nature of existence. The ramifications of wave-particle duality extend across various fields, from quantum computing to cosmology. In the realm of quantum computing, the wave-like superposition of qubits, quantum bits, enables the execution of multiple calculations at once, heralding an era of unparalleled computational capability. In cosmology, the concept of wave-particle duality aids in elucidating phenomena such as the cosmic microwave background radiation and the behavior of particles in the universe's infancy. However, the most significant implications of wave-particle duality may be philosophical. It challenges traditional notions of determinism and objective reality, proposing that the universe, at its core, is not merely a collection of separate entities, but rather a complex web of probabilities and interconnections. This perspective compels us to move beyond binary classifications of wave or particle, this or that, and to adopt a more sophisticated understanding of existence. Furthermore, wave-particle duality prompts us to consider the constraints of human perception. Our daily experiences are governed by classical physics, where objects possess clear properties and paths. In contrast, quantum mechanics operates in a domain where such certainties fade, and entities exist in a state of uncertainty until they are observed. This distinction serves as a reminder that our intuitions, shaped by macroscopic experiences, may not adequately capture the true essence of the universe. Despite its achievements, wave-particle duality continues to be a vibrant field of inquiry and discussion, with various interpretations of quantum mechanics providing differing insights into the nature of duality. The Copenhagen interpretation acknowledges the inherent probabilistic nature of quantum mechanics and the essential collapse of the wave function during measurement. In contrast, The many worlds interpretation suggests that all potential outcomes occur simultaneously in parallel universes, thereby negating the necessity for collapse. Other interpretations, such as Bohmian mechanics, introduce hidden variables to restore determinism while maintaining the concept of wave-particle duality. This duality also raises questions regarding the interplay between quantum mechanics and relativity. While quantum mechanics explains the behavior of particles at microscopic levels, general relativity describes the large-scale structure of space-time. Achieving a unified framework that reconciles these two theories remains one of the most significant challenges in physics, with wave-particle duality potentially offering insights into this complex issue. Ultimately, wave-particle duality transcends a mere scientific principle. It serves as a profound reminder of the universe's intricacies and mysteries. It illustrates that reality may not always be as it appears, and that comprehending the cosmos demands humility, creativity, and a willingness to embrace the unknown. By accepting wave-particle duality, we move closer to deciphering the mysteries of existence, one wave and one particle at a time. Fundamental particle. Fundamental particles are the building blocks of everything we see in the universe, from the smallest grain of sand to the largest galaxies. Despite their significance, are notoriously elusive and challenging to comprehend. They do not conform to the behaviors we observe in our everyday experiences, and our classical understanding often falls short when we attempt to visualize them. To grasp the true essence of fundamental particles, we must delve into the strange and intricate realm of quantum mechanics. At its essence, a fundamental particle is defined as the smallest unit of matter that cannot be subdivided into simpler components. For centuries, scientists held the belief that atoms were the ultimate constituents of matter. However, as advancements in physics progressed, it became evident that atoms themselves are composed of even smaller particles, which not only serve as the foundation of all matter, but also provide insight into the forces that govern the universe. The narrative begins with the identification of the atom in the early 19th century, when John Dalton proposed that all matter consisted of indivisible particles he termed atoms. Yet it soon became apparent to scientists that atoms were not truly indivisible. In the early 20th century, experiments conducted by scientists such as J.J. Thomson, Ernest Rutherford, and Niels Bohr demonstrated that atoms consist of a nucleus containing protons and neutrons, surrounded by a cloud of electrons. This revelation paved the way for the next phase of particle research, the investigation of subatomic particles. As technology progressed, particularly with the introduction of particle accelerators, physicists began to uncover an array of even more enigmatic particles. These experiments revealed that protons, neutrons, and electrons were not the ultimate components. Rather, they were made up of even smaller particles. This discovery led to the formulation of the Standard Model of particle physics, which outlines the fundamental particles constituting all matter and the forces that influence them. There are 6 varieties of quarks: up, down, charm, strange, top and bottom, as well as 6 types of leptons, which include the electron, muon, and tau-tau, along with their associated neutrinos. Quarks are never found in isolation. They always group together to form composite particles such as protons and neutrons. In contrast, electrons are stable particles that orbit atomic nuclei and play a crucial role in chemical reactions. Quarks are bound together by the strong nuclear force, which is mediated by particles known as gluons. This force is exceptionally strong at short distances, which is why quarks remain confined within larger particles like protons and neutrons. Although gluons are massless, they possess a property called color charge, which dictates how quarks interact with each other. This concept of color charge is similar to electric charge but operates on a different scale and is specific to the strong force. Leptons, however, do not experience the strong force. Instead, they interact via the electromagnetic force and the weak nuclear force. For example, Electrons engage with the electromagnetic force, which is responsible for electricity and magnetism, while neutrinos interact through the weak force, which is involved in certain types of radioactive decay. Despite being extremely elusive and challenging to detect, neutrinos are among the most abundant particles in the universe. Bosons serve as the force carriers of nature, while fermions constitute matter. Bosons mediate the forces that govern interactions between particles. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are each mediated by different bosons. For instance, the photon is the boson responsible for carrying the electromagnetic force, while the W and Z bosons mediate the weak nuclear force, which governs processes such as radioactive decay. The gluon, as previously noted, serves as the force carrier for the strong nuclear force. The Higgs boson, which was discovered in 2012, is linked to the Higgs field, responsible for imparting mass to particles. Among these, the Higgs boson holds particular significance as it elucidates the reason some particles possess mass while others do not. According to the Higgs mechanism, particles acquire mass through their interaction with the Higgs field. The intensity of this interaction determines the mass of the particle. The discovery of the Higgs boson at CERN marked a monumental milestone in particle physics, confirming the existence of the Higgs field and aiding in the completion of the Standard Model. However, despite its success in elucidating fundamental particles and forces, the Standard Model is not the ultimate explanation in particle physics, as it remains incomplete in several critical aspects. Notably, it does not incorporate gravity, which is described by Einstein's theory of general relativity. Additionally, the Standard Model fails to account for dark matter and dark energy, which constitute the majority of the universe's mass and energy, yet remain largely undetectable. Furthermore, the model depends on certain parameters, such as particle masses, that appear arbitrary and lack theoretical justification. This gap has prompted the pursuit of new physics beyond the Standard Model, with physicists actively seeking to broaden our comprehension of fundamental particles and their interactions. One of the most promising concepts in this endeavor is string theory, which suggests that particles are not merely point-like entities, but rather tiny, vibrating strings. These strings can oscillate in various ways, with different vibrational modes corresponding to distinct particles. If string theory holds true, it could provide insights into the behavior of natural forces and establish a unified framework that integrates all fundamental forces, including gravity. An additional focus of active research is the investigation of neutrinos, which are enigmatic particles that have puzzled scientists for decades. Their discovery has prompted numerous inquiries regarding the fundamental nature of the universe. Neutrinos possess mass, albeit a minuscule amount, and they interact only weakly with other forms of matter. In fact, trillions of neutrinos pass through the human body every second without detection. Gaining a deeper understanding of neutrinos and their significance in the universe could pave the way for new research opportunities in particle physics. The quest for dark matter represents another significant frontier in fundamental particle physics. Although we cannot directly observe dark matter, its existence is inferred from its gravitational influence on visible matter. Dark matter is believed to constitute approximately 27% of the universe's total mass and energy. Some researchers speculate that dark matter may consist of yet-to-be-discovered particles, such as weakly interacting massive particles, WIMPs. Identifying these particles could reveal the secrets of dark matter and transform our comprehension of the cosmos. As we delve deeper into the nature of fundamental particles, we are continually prompted to reevaluate our concepts of space, time, and reality itself. The more we uncover about these minute building blocks of the universe, the more we recognize the vast unknowns that remain. Are there other undiscovered particles awaiting revelation? Are there new forces yet to be identified? The pursuit of answers to these questions represents one of the most thrilling and significant endeavors in contemporary science. Ultimately, the exploration of fundamental particles transcends merely understanding the components of matter. It is about grasping the very essence of the universe. By unraveling the mysteries of the smallest particles, we move closer to comprehending the profound truths regarding the nature of reality, the forces that shape our world, and the origins of the cosmos itself. This journey to uncover these secrets is ongoing, and each discovery brings us one step nearer to unlocking the deepest enigmas of existence. Special relativity. Imagine you're on a train moving at high speed, looking out the window. The scenery flies by, and everything feels normal inside the train. But if someone outside the train saw you, it would look very different. They'd see you moving at high speed past them. Yet inside the train, it feels like you're still. This difference in how motion is experienced, depending on your perspective, is at the heart of Einstein's theory of special relativity. Special relativity changed our understanding of space and time. It tells us that the laws of physics are the same for everyone, no matter how fast they're moving, as long as they're not accelerating. This might sound simple, but it leads to surprising conclusions. The theory shows that space and time aren't fixed but flexible. They stretch and shrink depending on how fast you move. A key part of special relativity is that the speed of light is always the same, no matter how fast you're moving. This is a big shift from how we think about speed. Imagine you're in a spaceship, shining a flashlight forward. If someone else in another spaceship is moving in the opposite direction, they might expect the light to pass them faster than the speed of light. But according to Einstein, the speed of light remains the same for both of you, 186,000 miles per second. This is a cornerstone of special relativity, and it leads to surprising results. Now let's look at space and time as one combined thing: space-time. Picture space-time as a fabric stretching across the universe. Objects with mass bend this fabric as they move. The faster an object moves, the more it bends space-time around it. As you approach the speed of light, time for you starts to slow down relative to someone at rest. Space also contracts in the direction you're moving. This is called time dilation and length contraction. With time dilation, if you're moving close to the speed of light in a spaceship, time for you slows down compared to someone on Earth. This has been proven in experiments. For example, if an astronaut travels at nearly the speed of light and then returns to Earth after several years, much more time will have passed on Earth. The astronaut might have aged only a few years, while decades have passed back home. The faster you go, the more pronounced this effect becomes, and at the speed of light, time would stop altogether. Next, length contraction. As you approach the speed of light, distances in the direction you're moving get shorter. For example, if you're traveling at high speed, the length of your spaceship would appear shorter to someone watching from outside. This happens only in the direction of motion. The width and height of the spaceship remain the same. This contraction isn't an illusion, it's a real effect that happens because space itself changes depending on how fast you're moving. In the classical view, space and time were absolute, meaning they were the same for everyone, no matter how fast you were moving. But in relativity, space and time are connected. They can bend and stretch depending on motion, which leads to effects like time dilation and length contraction. It's not that time or space is slower or shorter in some absolute sense, but that their experience changes based on your speed. This idea of space-time being flexible is different from what we're used to, but it's been proven many times, especially with particles moving close to the speed of light. For instance, when cosmic rays hit the atmosphere, they create particles called muons that travel quickly. Because of time dilation, these muons live longer than they would if they were at rest, and they can reach Earth's surface before decaying. This confirms time dilation and supports special relativity. Another important result of special relativity is that nothing can move faster than the speed of light. As you approach the speed of light, the energy needed to keep speeding up increases without limit. It would take infinite energy to reach the speed of light, so it's impossible to go faster than that. This sets an upper limit on how fast objects or information can travel. It means we can't communicate faster than light. which puts limits on how we explore the universe or send information across vast distances. Despite seeming strange, special relativity has been thoroughly tested and confirmed. It's one of the most important theories in physics, and it's the basis for much of modern physics, including general relativity and even technologies like GPS. Even though the ideas in special relativity are counterintuitive and challenge how we experience the world, they shape the universe in ways we can't ignore. Special relativity shows us that space, time, and motion behave differently at high speeds, and its effects are felt even in everyday life. Event horizon. The event horizon is one of the most fascinating and mysterious features in the universe. It marks a critical boundary beyond which nothing, not even light, can escape the immense gravitational pull of a black hole. Despite its importance in understanding black holes and the nature of space-time, the event horizon remains a concept that defies intuition, inviting deeper exploration into the fundamental nature of the universe. At its core, the event horizon is not a physical surface, like the outer shell of a planet or a star, but a boundary in space-time. This boundary indicates the point beyond which escape from the black hole becomes impossible. The defining characteristic of the event horizon is that the escape velocity at this point exceeds the speed of light. This means that even light, which travels at approximately 300,000 kilometers per second, cannot escape once it crosses the event horizon. Once an object crosses this boundary, it is inexorably drawn toward the singularity at the black hole's center, where space-time curvature becomes infinite. To understand this better, let's consider gravity and how it operates near a black hole. A black hole forms when a star of substantial mass collapses under its own gravity. When this collapse happens, the star's core is crushed to a point of infinite density, and its gravitational pull becomes so intense that it warps the fabric of space and time itself. The event horizon is the boundary where gravity is so powerful that no object or signal can escape once it has passed this point. Imagine standing on the edge of a waterfall. As you approach, you feel the current pushing you forward. You could resist and turn back, but once you step over the edge, gravity takes control, pulling you down the waterfall without the possibility of returning. The event horizon works similarly. Once you cross it, the black hole's pull is so strong that no force, not even light, can overcome it. The relationship between the event horizon, time, and space adds another layer of complexity. According to Einstein's theory of general relativity, massive objects distort space-time, and the more massive the object, the greater the distortion. Black holes are so dense that they warp space-time to an extreme degree, causing the usual rules of physics to break down. The event horizon marks the point where this distortion becomes so severe that time, space, and the laws of physics behave in ways beyond our normal understanding. One of the most intriguing effects is that time appears to slow down as an object approaches the event horizon. To an outside observer, an object falling toward the black hole slows down as it nears the event horizon, appearing to freeze just before crossing it. However, from the perspective of the object itself, it crosses the event horizon without noticing any change in its experience of time. This difference occurs because of the warped nature of space-time near the black hole. The size of the event horizon is not fixed. It depends on the mass of the black hole. A more massive black hole has a larger event horizon, while a smaller one has a smaller one. This size is known as the Schwarzschild radius, named after the physicist who derived the equations describing black holes. The Schwarzschild radius is proportional to the black hole's mass and represents the critical distance from the singularity, where the escape velocity exceeds the speed of light. Although the event horizon is fascinating, it's important to recognize that it is not an absolute edge in the traditional sense. It doesn't represent a solid surface that an object would crash into. Instead, it marks a threshold in space-time that separates the observable universe from the hidden interior of the black hole. Once something crosses the event horizon, it is effectively cut off from the rest of the universe, and any information about it is lost. This leads to the famous black hole information paradox, where quantum mechanics suggests that information cannot be destroyed, but crossing the event horizon seems to destroy all information, creating a conflict between quantum mechanics and general relativity. This paradox has sparked years of debate among physicists. One proposed solution involves the idea of information scrambling at the event horizon. This theory suggests that information isn't lost, but becomes encoded in the black hole's quantum state in a scrambled form that could eventually be recovered. The event horizon is not just a theoretical concept. In 2019, the Event Horizon Telescope, EHT collaboration, made history by capturing the first-ever image of a black hole's event horizon. Using a network of radio telescopes across the globe, scientists observed the supermassive black hole at the center of the galaxy M87. The resulting image showed a bright ring of light surrounding a dark center, revealing the shadow of the event horizon. This breakthrough confirmed several predictions of general relativity and significantly advanced our understanding of black holes. In addition to black holes, event horizons also offer valuable insights into the broader study of the universe. Black holes and the event horizons that define them serve as natural laboratories for testing the limits of physics. By studying objects near the event horizon, scientists hope to uncover new insights into the nature of space-time, gravity, and information, and to potentially reconcile quantum mechanics with general relativity. The study of event horizons also offers a glimpse into the ultimate fate of the universe. As galaxies move apart in the expanding universe, distant objects will eventually pass beyond the event horizon of the universe itself. In this scenario, the entire universe would appear as a black hole to any distant observer, and no information from the outside universe would be able to reach those inside. This cosmic event horizon would mark the final boundary of space-time, where no light or matter could escape. The event horizon is a powerful symbol of the limits of human knowledge. It represents a threshold beyond which we cannot see, hear, or understand. It reminds us that there are parts of the universe that remain forever hidden from even our most sophisticated instruments. Yet paradoxically, studying event horizons brings us closer to understanding the deepest mysteries of the cosmos. By exploring the edges of black holes and the nature of space-time, we gain insights into the structure of reality itself. The event horizon challenges our perceptions and invites us to embrace the unknown, symbolizing the frontier of science where new discoveries await. Dark matter. Dark matter is one of the most fascinating and mysterious ideas in modern physics. It is a substance that accounts for about 27% of the universe, but is invisible. It doesn't emit, absorb, or reflect light, which is why it's called dark. Despite being unseen, dark matter has a gravitational effect on regular matter, influencing the movement of stars and galaxies in ways that can't be explained by the visible matter alone. In fact, it's the presence of dark matter that prevents galaxies from tearing apart due to their fast rotation. Without it, our current view of the universe would not hold up. The story of dark matter began in the 1930 seconds, when Swiss astronomer Fritz Zwicky made an unusual observation while studying the Coma galaxy cluster. He found that the galaxies in the cluster were moving far faster than expected based on the visible matter present. According to Newton's laws, they should have been flying apart, but they weren't. Zwicky suggested that some unseen substance was pulling the galaxies together, which he called dark matter, though its exact nature remained a mystery. In the 1970 seconds, American astronomer Vera Rubin observed the rotation curves of galaxies, which plot the speed of stars at different distances from the galaxy's center. According to Newtonian physics, stars farther from the center should move more slowly due to a weaker gravitational pull, but Rubin found that stars at the edges of galaxies were moving just as fast as those near the center. This discrepancy suggested that there was more mass in galaxies than could be seen, providing further evidence for dark matter. But how can we detect dark matter if it doesn't interact with light or other electromagnetic forces? The key lies in its gravitational effects on visible matter. We can observe how galaxies and clusters of galaxies behave and deduce the presence of dark matter from these effects. Because dark matter does not interact with light, it doesn't fit into our usual categories of matter, which include protons, neutrons, and electrons, the particles that make up atoms. So, what exactly is dark matter? Several leading theories exist, with one of the most popular being weakly interacting massive particles, WIMPs. These hypothetical particles are thought to have mass, which is why they exert gravity, but they interact weakly with ordinary matter, which is why they don't emit or absorb light. WIMPs could be detected through their gravitational effects or through rare interactions with normal matter, but despite extensive searches, they have not yet been observed. Another possibility is axions, much lighter particles proposed as a solution to the strong CP problem in physics. Like WIMPs, axions are weakly interacting and do not emit light, but they have different properties, such as being very low in mass, making them harder to detect. However, their abundance could still explain the gravitational effects we observe in galaxies and clusters. In addition to these particle-based theories, some propose modifications to our understanding of gravity itself. For example, the modified Newtonian dynamics, MOND theory, suggests that the laws of gravity change at very large distances, especially in the outer regions of galaxies. According to MOND, the need for dark matter might stem from how gravity behaves at these extreme scales, rather than from the presence of invisible matter. However, this theory has not yet fully explained all the observations, and most physicists favor the idea that dark matter is an unknown particle rather than a modification of gravity. The existence of dark matter has also been inferred from the study of the universe's large-scale structures. The cosmic web made up of galaxies, clusters, and filaments would not have formed as it has without dark matter. In the early universe, dark matter's gravitational influence helped pull ordinary matter together, leading to the formation of the first galaxies and clusters. Without this unseen mass, galaxy formation would have been slower, and the universe would look very different today. One of the strongest pieces of evidence for dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. When light from a distant galaxy or star passes near a massive object, the object's gravitational field bends the light, a process called gravitational lensing. This effect allows us to map the mass distribution in the universe, even when that mass is invisible. Studies of gravitational lensing have shown that galaxy clusters contain more mass than can be accounted for by visible matter alone, providing more proof of dark matter's presence. Though dark matter exerts a significant gravitational influence, it does not interact with electromagnetic forces, meaning it can't be detected by conventional telescopes. We can't see it directly, but we can infer its presence from its effects on visible matter. One of the challenges in studying dark matter is that it exists everywhere, yet is undetectable using traditional methods. It shapes the structure of the universe, but we cannot directly observe it. One exciting area of research is the possible connection between dark matter and dark energy. While dark matter is thought to account for 27% of the universe's energy, dark energy makes up about 68% and is responsible for the universe's accelerated expansion. Some theorists believe that dark matter and dark energy may be linked, and understanding one could provide insights into the other. The deeper mystery, however, is why dark matter exists in the first place. What role does it play in the universe's evolution? If we understand dark matter, could we solve other cosmic puzzles, like the formation of galaxies or the behavior of gravity at large scales? The search for dark matter continues to push the limits of science. Experiments are underway to detect it directly, using highly sensitive detectors placed deep underground, shielded from cosmic radiation. Observatories are also studying the cosmic microwave background, the afterglow of the Big Bang, for clues about how dark matter influenced the early universe. Theoretical physicists are developing new models to understand how dark matter fits into the framework of particle physics and cosmology. While we can't yet see dark matter, we know it is there, shaping the universe in profound ways. When its true nature is revealed, it could change our understanding of the cosmos. Until then, dark matter remains a fascinating mystery,
one that challenges our understanding of physics and promises to uncover new truths about reality itself.
Schrödinger's Cat Paradox. Schrödinger's cat represents one of the most renowned thought experiments in quantum mechanics, often employed to illustrate the paradoxical and counterintuitive aspects of quantum theory. However, what is its true significance? How does it challenge our perception of reality? And why has it generated extensive debate since its inception? At first glance, the notion of a cat simultaneously existing in two opposing states, alive and dead, appears nonsensical. Yet this paradox delves deeply into the essence of observation, the observer's role, and the fundamental principles governing the quantum realm. Austrian physicist Erwin Schrödinger devised this thought experiment in 1935 as a critique of the Copenhagen interpretation of quantum mechanics, which was the prevailing theory at that time. The Copenhagen interpretation posits that quantum systems exist in a superposition of states until they are observed or measured, at which point their wave function collapses into a definitive state. In this framework, Schrödinger's cat serves as a means to investigate the peculiar and often illogical consequences of this theory when applied to macroscopic entities, such as a cat. Consider the following scenario. A cat is enclosed in a sealed box alongside a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The arrangement is such that if the Geiger counter detects radiation, a random quantum event, it activates the hammer, which shatters the vial of poison, resulting in the cat's death. Conversely, if no radiation is detected, the cat remains alive. Due to the inherent quantum uncertainty of the radioactive atom, it exists in a superposition of decayed and undecayed states, according to quantum mechanics, until the box is opened and the system is observed. Consequently, the atom is both decayed and not decayed, leading to the conclusion that the cat is simultaneously alive and dead. This encapsulates the paradox. In the quantum realm, particles such as electrons or photons can exist in multiple states at once, a phenomenon referred to as superposition. However, when these concepts are applied to a cat, which undeniably exists in one specific state or another, our intuition falters. The notion that a cat can be both alive and dead simultaneously appears absurd and implausible. Yet quantum mechanics seems indifferent to our classical intuitions. The essence of Schrödinger's cat paradox resides in the interpretation of quantum mechanics. According to the Copenhagen interpretation, when the system is unobserved, all potential states, alive or dead, exist in a superposition. It is only upon measurement, that is, when the box is opened and an observer looks inside, that the wave function collapses into a single state. The process of this collapse, including how and why a quantum system selects a specific state, remains one of the profound mysteries of quantum mechanics. In the Schrödinger's cat thought experiment, prior to the box being opened, the cat exists in a superposition of both alive and dead. This raises a significant dilemma. How can a cat, a macroscopic entity, exist in such an unusual quantum state? In our observable world, objects are either alive or dead, not both. This contradiction indicates a fundamental challenge in applying quantum mechanics to larger, everyday objects. One potential explanation is that quantum superposition is primarily applicable to microscopic particles, such as electrons or atoms. In contrast, macroscopic objects like cats consist of a vast number of particles, and the interactions among these particles with their environment lead to decoherence. Decoherence refers to the phenomenon where quantum superposition ceases to exist as a system becomes entangled with its environment, leading to classical behavior. For instance, while the atom within the box may exist in a superposition of states, the cat, as part of a larger system, will undergo decoherence and will be perceived as either alive or dead, but not both. This situation prompts further inquiry into what constitutes an observer. The Copenhagen interpretation posits that the wave function collapses when a measurement or observation is made, yet this raises profound questions regarding the role of consciousness in the quantum realm. Does the state of the cat depend on whether a human opens the box, or does any environmental interaction, even without human observation, lead to the collapse of the wave function? Some interpretations, such as the many worlds hypothesis, propose that all potential outcomes of a quantum event occur, each in its own parallel universe. In the scenario of Schrödinger's cat, one universe would have the cat alive, while another would have it dead. In this view, the observer does not collapse the wave function. Rather, they experience only one of the possible outcomes, with the other branches existing in separate realities. Conversely, objective collapse theories suggest that the wave function does not collapse solely upon observation, but rather undergoes spontaneous collapse when it reaches a specific level of complexity. In these interpretations, the cat could remain in a state of being both alive and dead until the system attains a critical threshold that necessitates collapse. Some physicists have even proposed that there may be a fundamental cause for the wave function's collapse that occurs independently of observation or measurement. The Schrödinger's cat paradox questions the very essence of reality, prompting us to consider what it means for an entity to exist in two states simultaneously. It challenges us to reconcile the probabilistic nature of the quantum realm with our daily experiences of clearly defined objects. Is reality inherently probabilistic, or is there a deeper deterministic framework that remains undiscovered? This thought experiment also highlights significant inquiries regarding the connection between quantum mechanics and classical physics. Why do large macroscopic entities, such as cats, conform to classical physics laws, while microscopic particles follow quantum mechanics? The interaction between quantum and classical realms is a pivotal focus in physics, with ongoing research aimed at understanding how classical behavior emerges from quantum systems. This exploration of the classical limit of quantum mechanics has led to intriguing advancements, including the investigation of quantum to classical transitions and the influence of decoherence on everyday occurrences. Furthermore, the Schrödinger's cat paradox has ramifications for quantum computing, as quantum computers utilize the principles of superposition and entanglement to execute calculations with far greater efficiency than their classical counterparts. In a quantum computer, qubits can simultaneously exist in a superposition of both 0 and 1, enabling these systems to execute numerous calculations at once. However, akin to Schrödinger's cat, quantum computers depend on the collapse of the wave function upon measurement. Understanding the timing and nature of this collapse is essential for ensuring the stability and reliability of quantum computing systems. Although the Schrödinger's cat thought experiment was initially conceived as a critique of quantum mechanics, it has evolved into a vital element of the quantum discourse. It compels us to confront the limitations of our intuition and to reevaluate our perceptions of reality, observation, and measurement. This thought experiment underscores the significant differences between our everyday experiences and the strange realm of quantum mechanics, where particles can exist in multiple states simultaneously, and the act of observation is crucial in determining outcomes. The Schrödinger's cat scenario remains a powerful instrument for investigating the foundations of quantum mechanics, illuminating the enigmas of superposition, wave function collapse, and the observer's role in the quantum realm. While it may appear to be an absurd situation, it challenges us to reconsider our fundamental beliefs about reality, making it one of the most significant and enduring concepts in contemporary physics. Quantum uncertainty. Quantum uncertainty represents one of the most significant and often misinterpreted concepts in physics, challenging our traditional perceptions of reality and compelling us to reconsider the fundamental nature of existence. At its core, this principle suggests that nature operates on a probabilistic basis at the quantum level. This is not merely a consequence of technological constraints or inadequate measurement instruments. Rather, it is an intrinsic characteristic of the universe. To grasp quantum uncertainty, consider the task of measuring the position and velocity of a car on a highway within the framework of classical physics. This process is relatively simple. You observe the car's location and speed, and from these two data points you can forecast its future position. However, the situation changes dramatically in the quantum realm. If the car were instead a quantum particle, attempting to measure its position with greater accuracy would result in a corresponding decrease in the certainty of its speed, and vice versa. This behavior is succinctly described by Werner Heisenberg's uncertainty principle, a foundational element of quantum mechanics. The uncertainty principle is frequently misconstrued as a mere limitation of our measurement capabilities, but its implications are far more profound. It is not simply that our measuring techniques are inadequate. Rather, the act of measurement itself alters the state of the system being observed. In classical physics, illuminating a moving object with a flashlight does not influence its motion. In contrast, in the quantum domain, observing a particle necessitates interaction, typically with photons or other particles, which inevitably disturbs the state of the particle. To illustrate this, imagine trying to find a small marble in a dark room by bouncing tennis balls off it. Each collision would displace the marble, making it impossible to accurately determine both its precise location and motion at the same time. This analogy, while not perfect, effectively highlights the essential trade-off between determining a particle's position and its momentum. The more precisely one is measured, the less certain the other becomes. At first glance, this uncertainty may appear to be a trivial aspect of physics, relevant only to scientists studying subatomic particles. However, its implications are profound and challenge the deterministic perspective of classical physics. In Newtonian mechanics, if one knows the position and velocity of every particle in the universe, it is theoretically possible to predict the future with complete accuracy. This concept, known as Laplace's determinism, stands in stark contrast to quantum uncertainty. At the quantum level, the universe operates not as a precise machine, but as a probabilistic system governed by probabilities and wave functions. A wave function serves as a mathematical representation of a quantum system, encapsulating the probabilities of various outcomes. When a particle is not being observed, its wave function reflects a range of potential states. For instance, an electron surrounding an atom does not occupy a single well-defined position. Rather, it exists as a cloud of probabilities, a diffuse area where it is likely to be located. This phenomenon is not merely a reflection of ignorance or incomplete data. It is a fundamental characteristic of quantum reality. The probabilistic nature of quantum mechanics becomes even more perplexing when we examine the measurement process. Prior to measurement, a particle exists in a superposition of states where multiple possibilities coexist. Upon measurement, the wave function collapses to yield a single outcome. For example, measuring the position of an electron results in the wave function collapsing to a specific location, eliminating all other possibilities. However, the reasons behind this collapse and the effects of measurement remain some of the most profound mysteries in quantum mechanics. Quantum uncertainty significantly influences our comprehension of energy and time. Just as there is a trade-off between position and momentum, a similar uncertainty relationship exists between energy and time. This principle permits temporary violations of energy conservation, resulting in phenomena such as virtual particles. These particles emerge and vanish almost instantaneously, playing a vital role in interactions between particles in a vacuum. Although they exist for only a brief moment, their effects can be observed and have tangible consequences, exemplified by the Casimir effect, where two uncharged plates in a vacuum are attracted to each other due to the energy of virtual particles. The ramifications of quantum uncertainty extend well beyond experimental settings. For instance, it is essential for the stability of atoms. Electrons cannot spiral into the nucleus as classical physics would suggest, because the uncertainty in their momentum would become infinitely large. This quantum indeterminacy establishes a balance that prevents the collapse of matter as we understand it. Furthermore, quantum uncertainty challenges our traditional notions of causality and locality. In classical physics, causes precede effects, and interactions are localized. However, in the quantum domain, particles can become entangled, creating a mysterious link where the state of one particle is instantaneously related to the state of another, regardless of the distance separating them. This phenomenon, known as quantum entanglement, does not contradict the uncertainty principle, but rather complements it, illustrating that the quantum realm operates under a fundamentally different set of rules compared to classical physics. Additionally, quantum uncertainty is crucial for technological innovations. For instance, quantum cryptography leverages the principles of quantum mechanics to establish secure communication channels. The intrinsic uncertainty present in quantum systems guarantees that any effort to intercept a quantum communication channel will disrupt the system and be detected. Similarly, quantum computing utilizes the probabilistic characteristics of quantum mechanics to execute calculations that far exceed the capabilities of classical computers. By encoding information in qubits, which can exist in superpositions of states, quantum computers are able to tackle complex problems more efficiently than traditional systems. However, despite these advancements, quantum uncertainty compels us to engage with significant philosophical inquiries. If reality, at its most fundamental level, is probabilistic, what implications does this have for concepts such as free will and determinism? Are the outcomes we observe genuinely random, or is there a deeper, undiscovered layer of reality? These questions resonate throughout the history of physics, from Einstein's well-known assertion that God does not play dice with the universe to modern discussions regarding the interpretation of quantum mechanics. The Copenhagen interpretation, one of the most widely accepted frameworks, embraces the probabilistic essence of quantum mechanics and regards the wave function as a complete representation of reality. In contrast, interpretations such as the many-worlds hypothesis propose that all potential outcomes of a quantum measurement occur in parallel universes, with the observer experiencing only one. Other theories, like Bohmian mechanics, introduce hidden variables to reinstate determinism, although these often necessitate the abandonment of the principle of locality. Furthermore, quantum uncertainty aligns with our comprehension of complexity and chaos in macroscopic systems. While classical chaos theory addresses deterministic systems that are extremely sensitive to initial conditions, quantum mechanics adds a layer of fundamental unpredictability. This interaction between chaos and uncertainty influences phenomena ranging from weather patterns to the behavior of complex molecules. Demonstrating that quantum principles can subtly yet significantly impact the macroscopic realm, quantum uncertainty transcends mere mathematical abstraction or a characteristic of microscopic particles. It serves as a glimpse into the essence of reality, unveiling a universe that is not fixed and deterministic, but rather dynamic and probabilistic, where possibilities surpass certainties and observation influences existence. This insight not only propels scientific advancement, but also encourages us to appreciate the mystery and awe of a cosmos governed by laws that defy our intuition and broaden our perspectives. Gravitational waves. Imagine standing by a calm pond. The water is still, reflecting the clear blue sky above. Then a stone is thrown into the pond, sending ripples across the surface. The ripples spread outward, distorting the once smooth surface. Now, picture instead of a stone, a far more massive event, like the collision of two black holes or the explosion of a supernova. and instead of a pond, it's the fabric of space-time itself. The ripples created by such cosmic events are called gravitational waves. Gravitational waves are one of the most profound predictions of Albert Einstein's theory of general relativity, offering a new way to observe the universe. In simple terms, gravitational waves are ripples in space-time that occur whenever massive objects accelerate, distorting the geometry of space and time. These waves travel at the speed of light, carrying information about some of the most energetic processes in the universe. For many years, gravitational waves were a purely theoretical concept, something scientists could not directly observe. It wasn't until 2015 that technology finally caught up, allowing scientists to detect these waves, marking a groundbreaking discovery in astrophysics. How did we reach this point, and why are these waves so extraordinary? To understand, let's first look at the theory behind gravitational waves. According to general relativity, space and time are not separate, but form a unified four-dimensional structure known as space-time. Objects with mass, like stars, planets, and black holes, warp space-time around them, much like how a heavy ball placed on a rubber sheet causes the sheet to bend. This warping is what we perceive as gravity. In the case of gravitational waves, massive objects, like two orbiting black holes, disturb the fabric of space-time, creating ripples that spread outward. As these ripples move, they stretch and compress space-time along their path. By the time they reach Earth, they cause tiny changes in the distance between objects. These changes are incredibly small, so small that only the most violent cosmic events, like the collision of supermassive black holes or the merging of neutron stars, can produce detectable gravitational waves. The idea of gravitational waves was first proposed by Einstein in 1915 as part of his general theory of relativity. He realized that accelerating massive objects, such as two orbiting stars, could send out waves of distortion through space-time itself. However, Einstein initially believed these waves would be so faint that they might never be detected. For decades, gravitational waves remained a theoretical concept until 2015, when scientists working with the Laser Interferometer Gravitational Wave Observatory, LIGO, made an astonishing announcement. They had detected gravitational waves for the first time, coming from the collision of two black holes about 1.3 billion light-years away. The signal picked up by LIGO's ultra-sensitive detectors was unmistakable, the sound of space-time itself being disturbed by one of the most cataclysmic events in the universe, the merger of two black holes. This discovery confirmed one of the key predictions of general relativity and opened a new era in astrophysics. But what exactly happens during a gravitational wave event? When two black holes, or other extremely dense objects, begin to orbit each other, they cause ripples in space-time. As they spiral closer together, these ripples become stronger, much like how waves in the pond get bigger as the stone sinks deeper into the water. When the black holes eventually merge, the resulting burst of energy sends gravitational waves through space. These waves carry information about the masses, spins, and the nature of the collision itself. Detecting gravitational waves requires incredibly sensitive equipment. LIGO's detectors use laser interferometry, where two laser beams are split and sent down long arms in perpendicular directions. When a gravitational wave passes through the detector, it stretches and compresses space-time, causing a tiny change in the distance between the laser beams. This change is extremely small, on the order of 1/10,000th the diameter of a proton, but it can be detected with astonishing precision. In the case of the 2015 detection, the signal from the black hole merger lasted only a fraction of a second, but in that brief moment, it provided a wealth of information about the event. The detection of gravitational waves wasn't just a scientific triumph, it was also a testament to human ingenuity. It was the result of decades of work from thousands of scientists and engineers. Gravitational waves don't just tell us about black holes, they offer a glimpse into the early universe. By studying these waves, scientists can learn about the formation of the first stars and galaxies and gain insight into extreme environments like the interior of neutron stars or the physics of black hole mergers. What makes gravitational waves so special? The key is that they carry information that's impossible to obtain through other means. For example, light, whether visible, ultraviolet, or infrared, can be blocked or distorted by dust and gas in space, making it difficult to study certain astronomical objects. Gravitational waves, however, can pass through anything, making them an incredibly powerful tool for astronomers. Since the first detection in 2015, LIGO and its counterpart Virgo have made several groundbreaking detections, including the collision of neutron stars. These discoveries have provided a new perspective on some of the universe's most violent events and promise to reveal even more in the years to come. Detecting gravitational waves comes with immense challenges. The changes in space-time caused by these waves are infinitesimally small, and the equipment required to measure them is incredibly delicate. For example, LIGO's detectors are designed to measure displacements as small as 1,000th the width of a proton. To achieve this precision, the system must also filter out noise from Earth-based sources like traffic, earthquakes, and even air molecules. Despite these challenges, the ability to detect gravitational waves has opened a new chapter in our understanding of the universe. It has provided a tool to observe the most extreme phenomena, from black hole mergers to neutron star collisions, offering valuable data that helps us refine our theories of gravity, space, and time. The discovery of gravitational waves is a reminder of how dynamic and mysterious the universe truly is. It shows how far human curiosity, ingenuity, and the relentless pursuit of knowledge can take us. As we continue to study these ripples in space-time, we will uncover new truths about the very fabric of the universe, truths that have been hidden from us for eons, waiting to be revealed by the waves of the cosmos. Information theory. Information theory is a fundamental yet often misunderstood discipline that significantly influences the contemporary world. At its essence, it examines how information is quantified, transmitted, and comprehended within a universe characterized by entropy and complexity. Although it may appear abstract, information theory is foundational to various fields, including the internet, telecommunications, biology, and quantum physics. Understanding its principles provides valuable insights into the core structure of reality. To illustrate its concepts, consider the game of 20 questions, where the goal is to identify an object by asking yes or no questions. Each question you pose eliminates certain possibilities, thereby narrowing the range of potential answers. The fewer questions required to identify the object, the more efficiently you are acquiring information. This game effectively demonstrates the core tenets of information theory, which involve quantifying uncertainty and conveying meaningful data. In the mid-20th century, Claude Shannon, often regarded as the father of information theory, formalized these concepts while working at Bell Labs. His mission was to enhance communication systems, such as telephone lines. Shannon recognized that the primary challenge was not merely the noise present in the communication channel, but also the intrinsic uncertainty associated with message transmission. His seminal 1948 paper, A Mathematical Theory of Communication, introduced the notion of information entropy, which quantifies the unpredictability or randomness of a message. A higher level of entropy indicates greater uncertainty or complexity in the information being conveyed. To further clarify, consider the act of flipping a fair coin, which has two equally likely outcomes, heads or tails. Each flip conveys one bit of information, a term coined by Shannon, representing a choice between these two outcomes. Now, envision a biased coin that lands on heads 90% of the time. The predictability of outcomes in each flip results in diminished information content. This principle elucidates why a sequence of random letters exhibits greater entropy and necessitates more bits for encoding compared to a coherent English sentence. Information theory extends beyond mere coin tosses. It examines the efficiency of message encoding and the constraints of transmission through noisy channels. A significant insight from Shannon's research is that every communication system has a maximum reliable transmission rate, referred to as channel capacity. For example, when sending a message over a poor-quality phone line, the channel capacity dictates the amount of information that can be transmitted accurately. Shannon showed that it is feasible to approach this capacity by encoding messages in a manner that mitigates noise, a concept that has formed the basis for error-correcting codes utilized in various technologies, from CDS to satellite communications. The elegance of information theory lies in its broad applicability. It is relevant not only to engineered systems, but also to natural phenomena. In biology, for instance, DNA functions as a communication channel where genetic information is encoded, transmitted, and decoded. The double helix structure efficiently carries instructions for protein synthesis and excels in information storage and replication. Mutations, which can be likened to noise in a communication channel, introduce variations that propel evolution. Information theory aids biologists in quantifying the complexity and fidelity of genetic messages, providing valuable insights into heredity and disease. In the field of neuroscience, information theory provides insights into how the brain processes sensory information. Our eyes, ears, and skin continuously receive signals from the environment, including light, sound, and touch. The brain must filter, encode, and interpret this overwhelming influx of data. For instance, the retina functions as a data compressor, transforming the extensive visual input into a manageable flow of signals directed to the brain. This mechanism resembles the compression algorithms utilized in digital images and videos, where redundant or less critical data is eliminated to conserve space. One of the most fascinating applications of information theory lies in its potential to elucidate the nature of reality. Theoretical physicists have begun to investigate the notion that the universe functions as a vast informational system, where physical laws resemble codes and space-time serves as a medium for data transmission. This viewpoint is particularly significant in quantum mechanics, where the concept of quantum information challenges conventional ideas of locality and causality. For example, quantum entanglement can be interpreted as a form of information transfer that transcends classical limitations, connecting particles instantaneously over great distances. Moreover, information theory underscores the boundaries of knowledge. The uncertainty principle in quantum mechanics, which asserts that certain pairs of properties, such as position and momentum, cannot be accurately measured at the same time, can be understood through the framework of information. It indicates a fundamental trade-off between the information we can acquire about one property versus another. Similarly, chaos theory in classical systems illustrates how minor uncertainties in initial conditions can exponentially amplify, rendering long-term predictions impossible, even in the presence of deterministic laws. One intriguing aspect of information theory is its connection to entropy in thermodynamics. At first glance, thermodynamic entropy, which measures the disorder of physical systems, and information entropy, which quantifies uncertainty in messages, may appear unrelated. However, they are fundamentally intertwined. In the 19th century, physicist Ludwig Boltzmann demonstrated that entropy is associated with the number of microscopic configurations that correspond to a macroscopic state. Shannon later expanded this concept into the field of information, illustrating that entropy serves as a measure of the information that is absent regarding a system state. This relationship has significant implications for our understanding of the flow of time, as the increase in entropy corresponds with the direction of time we perceive. In today's digital era, Information theory is foundational to technologies that have revolutionized society. The Internet, for instance, depends on protocols that efficiently encode, transmit, and decode vast quantities of data. Video streaming services, online communication, and even artificial intelligence are all products of principles initially proposed by Shannon. Compression algorithms, such as those utilized in JPEG images or MP3 audio files, minimize file sizes without compromising quality by removing redundant data. These algorithms exemplify the trade-offs and efficiencies central to information theory. Despite its widespread application, information theory continues to evolve. Researchers are investigating its potential in emerging fields like quantum computing, where information is represented by quantum bits, or qubits, which can exist in multiple states simultaneously. Unlike classical bits, which can only be either 0 or 1, qubits can embody numerous possibilities at once, paving the way for extraordinary computational capabilities. Quantum systems are notably vulnerable to noise, and effectively correcting errors within these systems necessitates a comprehensive grasp of both classical and quantum information theory. As we delve deeper into the nature of information, it becomes increasingly evident that it transcends mere utility in understanding communication systems or developing technology. Information is a fundamental element of the universe, intricately connecting physics, biology, and human experience. From the genetic codes embedded in our DNA to the algorithms steering spacecraft toward distant planets, information profoundly and subtly influences our reality. Information theory reveals that at the core of complexity lies a simple yet elegant truth. The universe is a conversation, and we are active participants in this dialogue.